about 22 years ago, something happened which changed pretty much everything we do, right from shopping, for entertainment, reading. And that was the development of the World Wide Web by Sir Tim Berners-Lee. And that was one development which has probably had the most impact in all the history of technology. A few years later, same person, and depending on from which perspective you come from, a bunch of others as well, came up with something which is known as the Semantic Web. The main idea was to come up with ways to describe the services and the data which was available on the web, which can be consumed automatically by agents or by any other technologies, so that a lot of the tasks can be automated. That was the classical example which was provided in the article in the magazine Semantic Web. But the core theme is still to provide additional metadata for describing the data and the services. It took a really long time. I mean, this story appeared again after 11 years, so it has been 11 years. But Google, one of the most popular search engine which pretty much everybody uses, they have started using a lot of the semantic web technologies in their search engine, although they do not call it semantic web technologies, but they still use it behind the scene. Especially after their acquisition of Freebase, they have started pulling out a lot of data which was available in Freebase and have started providing it in their search results, which is known as the Google Knowledge Graph. And again, a development which happened sometime last year, IBM Watson came into the limelight for defeating a bunch of humans on the quiz show Jeopardy, where it was way ahead of all the humans. And later on it was revealed that actually even IBM Watson was utilizing some of the semantic web technologies. But a lot of it was behind the scene, and nobody knows exactly how much portion of, or what kind of semantic web technologies they were using. The point being that semantic web technologies, since its development, have picked up, and it has led to a lot of useful inventions and developments. Another example, Siri, using a lot of the semantic web technologies and the data which is available on the web. In 2006, the same person who came up with the idea of semantic web or the web, Sir Tim Berners-Lee, he came up with 4 simple ideas to make semantic web mainstream and being able to publish the data which is available on the web, so that it's accessible to a lot of people and it's also reused. And these principles were very, very basic. The first one was use URIs as names for things. Then the second one was make these URIs dereferenceable. So if somebody clicks on that URI using the browser or using the Sparkle query, then it actually retrieves some data. Then make your data accessible using the Sparkle endpoint or any other querying mechanism which you provide. And the most important of all was include links to other URIs or other data sets in some way or the other, so that people can traverse from one data set to another one, just as you would traverse on the World Wide Web by clicking on the hyperlinks. What this has allowed is, this is still an old picture, but what this has allowed is the development of these interlinked RDF-based data sets primarily, which is known as the linked open data cloud. These data sets consist of a whole lot of diverse domains. They are owned by independent data providers. They are coming from private companies, they're coming from government agencies, they're coming from nonprofits. The thing is, just like the World Wide Web exploded, the semantic web data sets have also begun to grow and they have started exploding. Primarily, these data sets, they are connected via the all-same-as relationship. That is, basically they're saying that this entity which is present in one data set is exactly identical to another entity in the second data set. And like I mentioned earlier, it's an excellent source for background knowledge. You can obtain a whole lot of information. For example, if you go to GeoNIMS and click on Dayton, you can get a whole lot of information. Where is Dayton located? What are the nearby universities? What are the nearby cities? And so on. And a lot of folks, they have started calling it the mainstream semantic web. So nobody's talking about, all the slow things which people complained about in the beginning, but everybody says, this bunch of data, these collection of data sets are what is mainstream semantic web now, on all the mailing list discussions and everything. But is it really mainstream semantic web? Because if you look at the original ideas of semantic web, and even if you go back into philosophy, there's a lot of discussion about being able to express the relationship between the models and between these data sets, especially between the instances of the classes which are being captured by this data. The second question which comes to my mind is, how do you do querying on these data sets without knowing these data sets intimately? Like, unless you go and start poking into each of these data sets and start looking into it, how do you go about querying them? And how do you do schema level reasoning over LOD cloud? I mean, this is something which probably a limited number of folks do, but still something which can be useful. And as of now, I do not see any support for this kind of infrastructure or the linked open data cloud. So bottom line is this really the mainstream semantic web as people are calling it? And if it's not, then what can be done to fix these things? So, like one of the papers which Dr. Jain has written in the past and which captures this idea that relationships are at the heart of semantics. If you don't have that, then it's extremely difficult to capture semantics. And since LOD cloud primarily consists of same as links, then we need to fix these issues so that other kinds of relationships can be captured and they can be expressed within these data sets. LOD datasets, they capture a lot of instance level relationships, but there is a significant lack of the class level relationships. For example, superclass, subclass equivalents, and so on. And the other question is, how do you go about finding these relationships? People who are familiar with semantic web technologies will suggest, why don't you go ahead and start using some of the ontology matching tools which are state of the art. And as I will show later on, some of these tools actually do not work on LOD datasets for various reasons. My dissertation proposal essentially captures these points and tries to come up with solutions for these problems. And I'll propose solutions as well as alleviate, I'll provide the problems as well as provide solutions for some of these unrelated issues. So this is the agenda. I go about motivation and significance of this research, some of the research questions which I ask, and then some of the solutions which I propose, state-of-the-art research work, and what I plan to do, and then questions and comments from the audience. If at any point of time anybody has any questions, please feel free to stop me. So like we discussed earlier, linked open data, it's essentially a set of best practices for publishing and connecting structured data on the web in the form of RDF or whatever you have. And this practice has been adopted by an increasing number of data providers in the past 5 years, and it has gone all over the globe. Recently, I heard that data publishers in Kenya have started putting their census data and government data on the linked open data cloud, and which was something which was very fascinating because till now it was only North America and Europe which were doing all this. And the latest count which I heard was 295 data sets with over 50 billion triples, but nobody knows exactly what this figure is. Even if you send a question to the mailing list, nobody knows exactly what's going on there. And it's not something which has just exploded overnight. If you look at the figure in 2007 May, it had maybe less than 10 data sets overall. And most of these were already well-known: music brains, geonames, US Census data, and all that. 2007 October, it ends up becoming close a little over 20. You have FOB, you have Wikipedia, you have RDF book mashup, Semantic Web conference corpus, and all that coming in. 2009, the diagram becomes bigger and bigger. And the trend continues. And this is a little older, September 2011, because they haven't refreshed the diagram yet, but as of now, there is a big chunk of the data which is coming from government. Then there is another big chunk which is geographic data. There's a set of data about publications, cross-domain licenses, and so on and so forth. And the total number of triples which people estimate is about 31 billion triples. But the question which comes to my mind is 6 years of existence of this technology. How many applications come to your mind? Can anybody name even a single application of this data set? people will say that Watson is probably one of those technologies which use linked open data sets. But there are two components to this story. One is that the only data set which was used by Watson team was Wikipedia and nothing else. And there is a reason for that. This is something which I have learned very recently, is the fact that they used only a very, very small chunk of the Wikipedia dataset. Not the entire Wikipedia dataset, not Freebase, nothing at all. And the reason was that they did not achieve any performance gain by using any other dataset. And this was mentioned to me by somebody who was one of the main Semantic Web researchers involved with the Watson team. And they said when they measured the performance gain by using some of the other LOD datasets, they were actually getting a lot of false answers, the information gain was going down. So the only thing which helped them was the Yago class hierarchy which was present in Wikipedia and nothing else.
Was this after the thing?
After the thing, as
was this after they won in the game show, or?
No, this was actually before they entered to the game show.
No.
So they were doing internal testing, and what I was told is that every single data set which they pushed in, they had to have a performance gain of at least 10%.
Yeah.
If they don't get it, then they will remove it, or they won't keep it at all.
I was wondering whether this information is still what the information which is the final in the final system, or whether they put more in.
So I cannot comment what is the final system, but what I did here was, this is like a month-old information,
right?
At least. And then the other thing is they have their own repository of structured data. I'm forgetting the name of that knowledge source and the language which they use. It starts with a K. But what they did was, before the Watson project even started, they had a separate project going on where they were collecting massive amount of information from the web and storing it in structured format. So almost, I would say 70% of the information which was going to Watson was coming from their own proprietary knowledge source, which other than them, nobody has access.
Right, which is kind of probably curated data, so it's in much nicer form.
Highly
so
curated
why would they
data.
use linked data if
Exactly.
they have actually more quality out there?
Exactly.
And they're not going to give that to anybody else.
I don't think so.
I think more integrated, right? Because when they bring the thing in, they will make sure that there's
Exactly.
integrated as possible.
So they were, I mentioned earlier, they were doing tests, strict tests, and they had to achieve 10% improvement at least in order to plug in any data set.
So the bottom line is that they did not use LOD and other things, and instead they used structured information that they had curated.
The only chunk of LOD which they had used was this Yago class hierarchy in Wikipedia, that's it. And a natural question to ask is, like, if this is such a big deal or such a big development in Semantic Web, then why is this thing going on? We stumbled upon this query a while ago when we were trying to work on some of the NSF-related research work, where we were just trying to identify. Find out all the Congress members who have voted no on environmental legislations in the past 4 years with high pollution industry in the congressional districts. And if you think about it, then all this data is actually available on the LOD. You have data about the senator voting records. You have from geonames, location of industries and everything. You have the same information from Wikipedia. But even with LOD, we were having a hard time answering this query. So we started analyzing as to why this was happening. And we noticed a very interesting form of modeling. And this is just one example where we noticed in GovTrack. This big giant picture which you see over here, it's a simple statement. It says Nancy Pelosi voted yes for the healthcare legislation in the Congress. And you will wonder, like, why do you need this kind of a structure and like almost 4 different nodes to express such a simple statement? Because the more complicated you're making, and especially by using RDFS labels when you should be actually using resources, and when you should be using labels instead of resources, so totally inverse modeling, it just becomes more convoluted and very difficult to understand. Another example, geonames. One of the first data sets, and it used to be one of my favorites a little while ago. So over here, you see that there are 2 different types of places. You have populated place, and you have religious populated place. anybody with even a little bit of training in semantic web technologies can probably identify and understand the fact that maybe these two shouldn't be subclass of each other. But they don't express it like that. Why? Nobody knows. Because primarily their intention was to collect a lot of and generate a lot of instance data, and that's about it. Even if you look at the way in which they have described the features, it looks like it should be subclass of PPL, PPLR, an additional letter at the end, and it becomes a subclass of. My research essentially focuses on fixing some of these issues and alleviating the issues of querying, better relationship identification on the LOD on the web. And the approach is pretty simple. I plan to use the knowledge which is contributed by users on the web or on the linked open data to solve some of these issues, like ontology integration, detection of better relationship across these data sets, and being able to query multiple data sets. And what I'm presenting is a small section of the entire research, because otherwise I'll probably not be able to cover it up in the allocated amount of time.
So it kind of appears that you are satisfying some form of ego by publishing your data on the web in the link open data, but you're not seeing enough value of hard work you might have to do to integrate all that with existing data.
I think what comes to my mind is the joke which they had on April 1st when they published the linked open numbers. They basically sent out an email saying that we have published the largest data set available on the linked open data cloud, and it had a bunch of integers in increasing order, and they said, this is the largest and nobody can beat this. And they had linked it to Wikipedia or some of the other data sets, and a lot of people actually bought into it, and fortunately or unfortunately, that data set is an actual part of LOD Cloud now. And I don't know what's the point of that. So you're absolutely right. I mean, they're basically just, oh, it's a cool thing, we will get a lot of publicity and let's put it over there. And there are tools which allow them to create links to other data sets, and it shows up on the bubble, and you get some hits.
So I think one of you guys should put up a meter that simply will talk about A, the interlinks, and other usage. A counter. It will be very popular, because it's not like that you put in that is important, but how much it gets used is important. Sanjay, think about it, your project.
There are actually two websites. I think one is LOD-stats.com or something, okay, which gives statistics about the various LOD datasets. And last week when I was trying to make these slides and put some stuff together, I sent an email and I asked, can somebody tell me what is the count of same as links which are available on the LOD cloud? I received like 3 different answers, and eventually there was a group in Germany, somebody contacted me from there, and they said for 40 data sets there are about, I don't know, like 20 million or something same as links. And that was, the answer was kind of shocking, because, and it didn't sound right to me, and I sent them an email asking them, is this really true? Because out of 295 you just have 40 data sets with 30 million links, and I haven't heard anything back from them yet. So they said it could be because of errors, but there was no justification what kind of errors, what's going on and all that.
It also depends on the number of links, the number of triples in the links, right? In the data sets.
What do you mean?
If you're taking large enough data sets, don't you think it is possible for 20 million same as links?
But only 40 out of 295, and they said this is the total collection.
40 would be the largest 40.
No, they were saying this is the total. So it didn't seem right, and I haven't received any more answers since then. Circling back, so like I said, LOD captures instance level relationship, but there is a significant lack of class level relationships which are present, such as superclass, subclass, equivalence, and so on. So the first problem which I try to address is exactly this. And the system or the approach which I have is called Bloom's, which is based on the idea of bootstrapping. And I'll explain in more detail. So Bloom's is a bootstrapping-based linked open data ontology matching system. And it has been developed specifically for linked open data ontologies. But as the results prove that it can actually also be used for other ontologies which were involved with the ontology matching benchmark and all that. And the main task of this tool is to identify schema-level links between these various linked open data sets. It can be used for aligning ontologies which belong to different domains, such as publication, entertainment, social networks, and all that. So unlike some of the other tools which are heavily restricted to one domain and do not work on others, this tool actually can be utilized for all other domains as well. Just to do a quick recap of some of the existing approaches which people usually have. This is not my work, this is from another paper which appeared in VLDB Journal a little while ago. So traditionally, schema matching approaches are of two different kinds. One is the individual matcher-based approach. The other one is where they take these individual matchers and they try to combine them into a single matcher. And these individual matchers, again, are of two different kinds, schema-based, instance-based. So the schema-based, like you can guess, only utilizes schema information in the instance. One will rely more on instances. And the schema level one, again, split into two different categories, element level, structure level, and then element level ones are, they use knowledge from coming out of the phrases, language-based techniques, then constraint-based like rules and all that, so on. Same thing applies even for instance-based. Now when you combine matchers, you can go two different ways. One is where you can do the composition manually, where you put them together by yourself and try to figure out, okay, what fits well. Or you can do an automatic composition, depending on the requirements which are arising, you can make them compose automatically. And when we use one of these approaches on our LOD ontology, we obtained pretty interesting results. We obtained that the class nation was equivalent to the class menstruation with a confidence of 0.9, which is one of the highest confidence which they could have mentioned in their results. And the other thing which we noticed was they performed extremely well on the established benchmarks which they had in the ontology alignment initiative, but they did not do so well if you throw in any new ontologies or new collection of data sets. And LOD ontologies, unlike the ontology matching benchmarks, they are of very, very different nature. They're not created by a single person. Actually, they have been created typically by community, by scraping from web pages, by using Python scripts to dump out databases and all that. And like we discussed earlier, the emphasis is on number of instances and not on the number of meaningful relationships. Something which I find to be missing in September Berners-Lee's 4 points is explicitly this thing, because the focus was on creating more and more instances and linking them, not on the way they were modeled. And the other thing is that they require solutions which are beyond syntactic and structural matching, which most of the existing matchers do. Like I mentioned earlier, we use community-generated data sets. But is it a natural question to ask is, why would you do that? Is it like pulling a rabbit out of a hat or something, or what? Auxiliary data sources like WordNet, Yago and all that, they have very, very limited coverage. They usually talk about one domain, and if you're going to a dictionary, then they have proper nouns and all that. And community-generated data, although it's noisy, but it's still rich in content, it has a good amount of structure involved in it, and it has a self-healing property. If you try to destroy anybody's page on Wikipedia, it usually comes back up within a matter of minutes, if not seconds. The other issue is that, or the other advantage is that the problems like ontology matching have a dimension of context associated with them. And usually with community-generated data, you will see that context is mentioned in a proper way in most of the scenarios. So even if you see any controversial Wikipedia article, like how many episodes of Star Wars are there, then they will mention that the different ideas by different people and so on. Now, if you specifically look at Wikipedia, which is what I use for my ontology matching approach, it has more than 2.9 million articles, and it is continuously expanded by 100,000 active editors all the time. And it allows you to express your point of view without anybody coming in and cutting you short. They might correct it. But at the same time, article correction and creation is an ongoing activity. There is no weekends, there is no New Year holiday and all Now, this approach for ontology matching using Wikipedia, it relies on the category hierarchy which are present in Wikipedia. What we utilize are the categories which are used to organize the entire Wikipedia project, or the articles. So, unless you have to use them, you typically don't notice, but if you go down on the bottom of the Wikipedia article, there are categories which are present. And these categories follow a very simple structure. The categories on the extreme left are more significant than the categories on the right. So the significance is essentially decreasing from left to right. You do not place the article in every single category to which it should be related to, but only the most significant one. Now, if you place an article in a specific category and that belongs to another category, the article automatically becomes a part of the other category. So there is some notion of transitivity involved in it. And the approach, the Bloom's approach, which uses this Wikipedia category hierarchy, it utilizes the very first step is to pre-process the input ontology. Removes the property restrictions, remove individuals, and all that. The next thing it does is it tokenizes the class names. And that is, it's going to remove the underscores, hyphens, and other delimiters which typically come when you are looking at class names. And it's going to break down the complex phrases. So for example, if you have a complex expression or a big word like semantic web, it should ideally be broken down into two separate phrases, semantic space web. Once you have that, then it identifies the article in Wikipedia corresponding to this particular concept. Now, a lot of times you may get multiple hits for the same phrase, for example, cricket. So something which I figured out later on is a way to use instance-related information. So if you have instances in the ontology, you can utilize that to narrow down which specific sense is the most appropriate one for that particular purpose. Once you have the article correctly identified, then you identify the Wikipedia categories in which this article falls in. So you use the web services and you start querying the categories to which it belongs to. And then you get the category for these categories and so on. And eventually what you have is a category hierarchy tree, which is going up to level 4. The reason why I prune it at level 4 is because after level 4, a lot of stuff in Wikipedia is interlinked because the categories are really abstract. They start dwelling into categories like philosophy, life, science, meaning of life, and all that. So everything starts becoming linked to everything. So based on my experiments, I noticed that only up to level 4, you will actually get good results, and if you go after that, you'll actually start having performance loss. These trees, which I call as the Bloom's trees, once they are created, they are used for comparisons between concepts. So for any class like S, any concept name called S, you will create the tree TS, and for class T, you will have the category TT. The next step is that we compare these two trees and we try to identify what are the common nodes which are present between them. And we identify the common nodes at the topmost level. So if you have one node which appears at level 2, but if the same node is appearing at level 4, we will take the one which appeared at level 2. Now, it might be confusing, as you will say that, hey, if it's that kind of a structure, then the node should not repeat. Actually, Wikipedia category hierarchy is more like a graph. So a lot of times, if you have seen a node at level 2, it might occur at level 4 as well. So you have to do a lot of pruning in order to shape it like a tree. And I have an example of this later on. Once you have that, then you compute what are the common nodes between these two trees. And you assign a score to both the trees by computing the overlap divided by the total number of nodes which you have seen. So for example, over here, if you have a concept called Jazz Festival, which appears in the music ontology, and event which appears in the BBC program ontology, what you will have is this expansion where Jazz Festival gets expanded to Jazz Festivals, which goes to music festivals, and it keeps expanding and so on. And the same thing happens even for event. Now what the system does is it tries to identify what are the common level nodes between these two trees. So over here you will have entertainment events, festivals, and social events. And in this case, and the same thing will happen even for the other tree. Now it's going to count the total number of nodes which are left in the tree after pruning the ones below this level. So you will have 1, 2, 3, and 4. And in this case, you will have 1, 2, 3, 4, 5. So you will have, in one scenario, you will have 3 over 4. The other case, you will have 3 over 5. So one case, you'll get the score 0.75, and the other case, you'll get score 0.6. Now, the intuition which we had was the fact that because this particular concept took more levels to become more abstract, therefore, this is more specific than this one. And on the basis of that, it becomes possible to predict with a certain amount of confidence that this concept is actually a subclass of this one. And later on, we were able to do an improvement where we were actually even able to utilize information which was coming from the web by parsing some of the web pages, executing queries on Bing to verify that Jazz Festival is exactly an event. So that even led to higher precision as well.
Okay. You mentioned that it gets more specific if it takes more number of levels to get to the same node?
It is more specific to begin with if it's going to take more and more levels to become generic enough as the other one. So over here, what you see is Jazz Festival. Over here, you have event, okay? This one, 1, 2, 3. This one, 1 and 2.
Right.
So that is why that one is more specific than that one. Because the categories are essentially capturing an abstraction of an instance or of a concept. So that is why, that's the simple intuition.
Okay.
You want to draw some arrows there somehow. They want to draw some arrows, I think. It's unclear that this is kind of upside down tree. Right?
Oh, so this is different than an ontology tree. Yes, yeah, this is different than an ontology tree. I should have clarified it earlier. So ontology trees usually they are very abstract on the top, and then they become more and more specific as you go down. And this was a confusion even when you were working on the paper. So yeah, this is.
We never flipped it. I don't know why.
It's
okay. Now I got it.
Okay. To evaluate this approach, we had two different matching. And the second one was, all right, we are able to do it on LOD, but what about the existing community benchmarks? As of now, I'm not presenting the results because I'm still in the process of doing some of the evaluation, but I'll be presenting it in my final dissertation defense. Now, going to the second issue which we have, that is saying that,
so you were just going to say, I just checked on stats.lod2.eu.
Okay.
I mean, they don't have all data sets there.
Right.
They only have some from some repository. Which one was the repository? CCAN, yeah, exactly. And they report about 870,000 I'll-same-as links over 35 data sets. That's only part of it. But that's significantly lower than the number they had given you earlier, which you objected to. About 870,000. The interesting thing is that also from the same page that on the ontologies they have only about 120,000 RDFs as subclass of relationships. So all same as outnumbers subclass of significantly on big data. It's an interesting concept. Anyway, I didn't want to.
No, I can understand that because it's like the number of concepts in a schema will be less than the number of instances.
Right, yeah. It just sees how heavily data skewed it is.
Yeah.
Yeah, and 120,000 is, I mean, there is really not much in terms of ontology.
Ontology, yeah.
That's essentially, yeah. Anyway, sorry.
So, coming back to the other issue and related to it is that primarily LOD consists of only these same as links and nothing else. That is basically saying this instance on this data set is same as this instance on the other data set. So the next work essentially tries to alleviate this issue by identifying a different kind of relationship, that is the part of relationship identification. A part of relationship, as you'll know, that it's a very fundamental relationship in most of semantic web or any ontology, which you will see, like even basic formal ontology or even in philosophy and all These relationships, such as part of and causality, can, if they're provided in these data sets, they can allow for more intelligent applications, such as Watson, or even for knowledge discovery, or even for doing things like if you're doing a protein-protein interaction, or what is the effect of drugs on a specific protein or a cell. But unfortunately, they are not part of the LOD data set as of now. So the approach which I have for this is called Plato, which is the part of relation finder on linked open data tool. The other reason I called it Plato was because he was one of the earliest guys to look into this particular issue in philosophy, part of relationship. The Plato approach, the very first thing which it does is that it generates all, first of all, it's going to generate pairs of strongly connected entities. And by that, what we mean is that in any given data set, you might have a situation where it's linked to a whole bunch of other instances, but you only want to pick up the ones which are strongly connected. So, for example, if you look on Freddie Mercury's Wikipedia page, then it might happen that the Wright State's Wikipedia page actually, it might refer to Freddie Mercury, but Freddie Mercury's page may not link back to Wright State University. So that's an example of weak linking, at least by the heuristics which we have. In other cases, you will have a situation like Freddie Mercury and Queen, they will both be linking to each other. So that's an instance of a strongly connected relationship. Now, the intuition for doing this is to minimize the number of pairs which we were processing with respect to identification of part of relationship. If we remove this component, then it might lead to probably higher recall. But the only issue with that, it will slow down the system very heavily. So we were identifying the pairs which were very heavily connected to each other. The next thing we do is we use the existing class information about that specific entity from its schema. So for example, for Freddie Mercury, it might say that he's a singer, he's an artist, and all that. And for Queen, it might say a band, group of musicians or artists, and so on. Once we have these class names, then we do a lookup in WordNet, and we try to identify what kind of lexicographer files are we able to identify for these things. We do not use the instances directly because you will not find an entry for Freddie Mercury in WordNet. And this step is helpful because what it does is it allows us to identify the fact that a band is a group of people or a collection of people, and a singer is a person and all that. And that's the kind of information you can get from this. The reason why I do that is because of this. I utilize something which is known as Winston's taxonomy. Winston's taxonomy is one of the most comprehensive categorization of the different part of relationship which are available in nature. What Winston did was he studied in linguistics what are the different types of part of relationships which occur and how can they be split into different categories. So for example, if you have a cup and it has a handle associated with it. So this is kind of a component integral object because over here, parts perform a specific function. They are not identical to the rest of the cup in terms of their appearance and all that. And you can actually separate this part from the whole. And still the whole is still going to have its own thing. And we also gave some patterns in text which represent this specific kind of part of relationship. And it did the same across and created this classification. So for place area, like Dayton is part of Ohio, feature activity, paying and shopping. Stuff and object, gin martini, and so on. So what I do is I utilize the text patterns and this section. In the second step, using the text patterns which were provided by Winston, as well as by doing some more search about these patterns on the web, we created a whole bunch of these linguistic cues which represent this relationship. And by using the pairs of instances which we had in the previous step, we generate these patterns, which are traditionally known as the Hearst patterns. And we start searching for them on the web. So using the Bing Web Service Web Search API, we are able to search for these on web pages and all that. And we only restrict it to the top 50 pages because we were doing the exact query. So even to get, like putting it in double quotes, so even to get 50 pages is usually a big deal. And the second thing is that we wanted to make sure that that pattern is actually present. If we use more sophisticated NLP-based techniques, then we might be able to get a higher recall and higher precision as well. But for now, our approach relies on strict matching of the terms. And then once we obtain these pages, we parse the page and we identify the occurrence of this pattern, and we are able to go back and assert into the ontology that X is a part of Y in a specific sense. So for example, cell wall and cellulose. We found 48 pages which said that cell wall is made of cellulose. And we found 10 pages which said on the contrary, that cellulose is made of cell wall. So because of the overwhelming majority of these, we are actually able to say that, hey, cell wall actually consists of cellulose. And because I was complaining about the lack of schema knowledge in the LOD, so we don't just restrict it to instances. Because we have information which says that cellulose is a type of entity and cell wall is a type of organism and all that, we can actually go back and create these kinds of restrictions which say the fact that which can assert actually schema level information. So, for example, not every artist belongs to a band, but every band has to have a few artists. So using our restrictions, we are actually able to even assert that kind of relationship and put that back into the knowledge base. The evaluation objective for this tool are threefold. We want to evaluate Plato as a tool for finding the different kinds of part of relationship which are provided by Winston. We want to be able to use Plato for identifying part of relationship within a specific data set. And we want to be able to identify the part of relationship across data sets. So this one, an example of this will be finding relationships between DBpedia. And an example of this will be finding relationships between DBpedia and Freebase, and what kind of relationships can we get. The ultimate objective of both Bloom's and Plato is to be able to create an upper level, an overarching schema which can capture this information, so that this overarching schema can be used for the different purposes such as reasoning, querying, and all that. As many of you might know, querying was the thing with which I started looking into linked open data, and then we started stumbling upon all these different issues, that there is a lack of relationships and all that. The idea is that we can probably utilize or extend some of the upper level ontologies such as Sumo or Dolce or Proton and align those ontologies with some of these data sets. Once we have that alignment present, then we can use the concepts from these upper level ontologies and express queries on this data set. And the system will be able to process the query, identify what are the specific components or what are the specific data sets to which this query should be sent to, split it up, get the results from the individual Sparkle endpoints, integrate them, and then present it back to the user. We have implemented an initial version of it, and we are experimenting with it, and we have submitted a paper to that for early days as well. And using some of this work, what we have been able to do is we have been able to have a good amount of outreach. So for Bloom's, we have had a paper at ISWC, as well as a poster at the Ontology Matching Workshop. We did an extension of Bloom's in terms of the Bloom's Plus, which utilizes a whole lot of contextual information. For that, we had a paper at ESWC, and we also had a small paper at the ICBO workshop. The Plato tool has been accepted for publication at this year's ACM Hypertext conference, which will be in a couple of weeks from now. And some of the other issues which we have identified with respect to the linked open data cloud, they have been published in the form of a vision paper in AAAI Spring Symposium. A work which captures some of the querying related issues which arise out of lack of these relationships was accepted at the Geospatial Conference in 2009. So the remaining work which I'm planning to do with respect to my research work is significant evaluation of Bloom's on some of these LOD ontologies, being able to evaluate Plato on different data sets and identify these part of relationships, Then something which is a work in progress with CERSI is automatic classification of data sets, being able to identify the genre of these data sets and to submit it somewhere. Work which is in progress as of now is property alignment on the linked open data cloud with Kalpa and Sanjay, and we're working on it, and hopefully we should have results pretty soon for this. And that's about it. Any questions, I'll be happy to answer.
A question came to my mind from your last diagram, like using blooms, you were saying, yeah, you can create upper level ontologies, like let's say for example Freebase and Wikipedia, then you try to make an upper level ontology and you just query that upper level ontology.
So it's like if you take, let's say, Sumo ontology, one of the upper level ontologies, okay, and you align it with, let's say, 15 or 10 of these data sets, then what you're able to do is, you don't have to look at each of those 10 or 15 data sets to query them, okay, because the alignments or the mappings are already present. So instead of knowing that Freebase represents, research papers as scientific publications, and DBpedia refers to it as conference papers, all you have to know is that these are papers using a concept from, let's say, Sumo. And you can use that term for your query. And the system will figure out the fact that research papers are actually a type of paper.
So will this help, LOD has a lot of duplicate instances, right?
Right.
So will blooms be able to help in reducing duplicates?
Yes, in certain sense it can help, because what you'll be able to do is, two parts of the story. One is that we had this idea a little while ago, which we discussed, was being able to utilize blooms as an instance matcher, but the thing was there were already way too many players in that field. So that was part of the reason why I did not push that much. And the second thing is, yes, it can definitely be used. Because what you have to do is, once you know that, hey, these two things are identical using Bloom's trees or whatever, then you can actually say that.
Right, yeah. Okay, if there are a lot of players in instance matching, right, are there players who take instances through an unified ontology, or in terms of the Bloom's ontology? Because you know that these are two similar categories, and then you are trying to.
I don't understand the question.
Let me rephrase it.
Okay.
So when you're doing alignment, right? You're saying that this particular category is the same as this particular category in two different data sets. Like the way you told the conference publications on is similar to the publications on the other data set, right? So are there people who have done saying that, okay, now we know that the instances of these two?
To the best of my knowledge, no.
Okay.
I don't know if anybody else has any additional insight about it. But to the best of my knowledge, no.
Yeah, because you already have a pre-work, so.
Right.
Most of the people who cite your work raise the question that your approach is highly rely on the Wikipedia.
Okay.
How would you justify it?
Well, it's possible to actually substitute Wikipedia. So the ontology matching poster which we had, it actually talked about using other data sets. There is a version which uses WordNet. So you can plug in other data sets, WordNet, Freebase, and all that. So any system or any data set source which has hierarchy, it can actually exploit that data sets. But the evaluations which we did, we used Wikipedia, and I guess they go through the paper and they will look at that fact. Put it like that, but it's possible to use it. Because the title of the poster is actually plug and play ontology matching system. So,
what do you think about agreement maker?
I knew it. Something to be evaluated with in my final thesis.
So you don't think anything about it yet?
You know what
I know what she has been saying around and all that, and it's kind of funny because so the person who was working on Agreement Maker, he asked for my help, and I helped him out, and he basically told me, okay, this is what my results look like, and what I remember is those results actually were at par, or if not inferior to our results. And then I see the final paper, which had completely different results than what I was informed. And I mean, I haven't done anything with respect to that in a while. Like, I haven't published anything with respect to this work, so I haven't given that justification. But for some reason, in like the past 3 or 4 works, they have picked up this work and they have been, I don't know, citing it pretty heavily, which is, I guess, in some sense, it's good. That is something which I definitely plan to evaluate.
What are they saying? I mean, obviously they're quicker, right? Because that's a no-brainer.
Right.
I mean, if we use the dumps, we'd be quicker as well, right? What are they claiming in their papers concerning precision recall values compared to ours? Are they using the same baselines we use, or
yes, they do, and they say that it's better.
Okay.
Like, I think if I remember correctly, it was 0.1 or 0.2 better than what we were saying in some of these cases.
Okay. And what's your guess why it's better?
I don't know.
Okay. But they're not disclosing yet a lot about how the thing is working, right?
So I think they have tried sending the papers. All the publications, I think, which they have gives a glimpse of their system. I don't think it gives a whole lot because they've usually been workshops. So.
This is from
Isabel Cruz. Isabel Cruz.
Oh, I think they have an ESWC paper this time.
Oh, so it's pretty recent.
Yes, it is pretty recent.
Hey, Kunal and Peter, do you guys have any questions? Corey?
None for me. None at this point.
Oh.
Yeah, I have a question. So what kind of computational efficiency are we talking about? Is there any computational analysis, or is it mostly evaluation is based on the quality of results?
So I focus primarily on the quality of the results. I have not focused so much on the efficiency of the system, and because when we started using all this or doing all this work, I mean, there was nothing to begin with. So that was the focus.
So is it exponential time, polynomial time? I mean,
so for blooms, I would say, because we take m. So if you have m concepts in one and the other one has n, so it's mn, because it's basically doing it for every single concept. With Plato, I think if it has, it depends on the number of pairs which are generated, and that is something which is difficult to predict. Worst case, it will be everything is related to everything, so probably the n squared, I would say.
So more polynomial time than exponential time.
How far are we to take this basic infrastructure to make and when doing integration, say here is an additional structured data. So let's hypothetically assume that music brains is not part of LOD.
Okay.
And then we explicitly say, all right, I have this additional knowledge base, and use it while you are integrating or finding matches in LOD. So I could basically explicitly apply existing background knowledge in looking for alignments in LOD.
So you're saying using kind of class level information for instance matching purpose, or?
It could be class level, it could be instance level, doesn't matter.
I mean, in principle, we can do that. The only reason why we didn't push for at least the instance level stuff was, like I mentioned earlier, Pawan had the same kind of question. Like there are way too many players in the same area of instance matching. So Lime, there are like 3 or 4 tools which are all trying to do instance matching.
No, but I'm not trying to do instance matching or bottom-up analysis issue. What I'm saying, so here's an example. NCBO has ontologies that are not part of LOD.
Okay.
But those ontologies are supposedly of good quality, and there is a web service.
Then definitely we can do it.
Then what I want to do is say I identify a specific subset of LOD, specific cluster, and say as you look for alignment here, also incorporate this external knowledge, because I trust that external knowledge is high quality, and include that in finding additional matches that may be not in that external knowledge base but in LOD, because apparently LOD has a lot of scraped data, a lot of data which is of potentially lower quality.
So I think it's kind of similar to what we had in one of the proposals of basically cleaning up the LOD cloud with respect to better quality data sources and all that. So once we have this infrastructure, if we'll have techniques for reasoning and all that, we might be able to do a better job at that. So we might be able to do it actually.
Is there a Google for LOD?
Just a related follow-on question. Do you have any sense, so right now most of the background knowledge that you're using, right, to support this alignment, it's mostly coming from, like you mentioned, right, community-generated economy, if you will.
Right.
So quality sometimes a little bit hit and miss, but the biggest advantage is the scale, right, and redundancy. Do you have any insight or sense as to if you were to try to use like more formal background knowledge sources, take for example, like Science, right? What kind of trade-off or advantages would you get, if any?
So again, there's one system which is called OMVIUO. I don't know how to pronounce it, but what they try to do is they explicitly use upper-level ontologies, which is slightly different than Psych, but they try to do that and they try to use it. And we compared it with their system as well, so that because their coverage was very limited, so their performance was low. But because you mentioned Psych, so I'm not sure, we might be able to actually get good performance with Psych, so that could be actually a good evaluation to do that, but I don't have any figures for that.
Okay, no, okay.
Thanks.
Is there a Google for LOD? So basically why I'm asking this question.
Okay, so even before you complete the question, so what we are trying to do with the automatic classification of data sets for LOD, that is exactly what we're trying to do, is essentially have a search service which can, if you type music, then it's basically going to give a ranked list. All right, this is the most appropriate data set when it comes to music, and this is the second most appropriate and all that. If you'll notice, then the other search engines, semantic web search engines which are there, like Cindy's or Google and all that, what they try to do is, if you type for the term, they will go and try to figure out, like, okay, I see the term music in the RDFS label somewhere, and they try to find it. But eventually the goal with what Sergi and I are trying to do is to have this Google kind of thing for LOD. What was that complete?
Yeah, so basically what I was thinking all through this is that, so LOD is just like, it's analogous to the web, basically.
Yes.
It's evolving, and then it has grown out of proportion that you can't manually, categorize it. And the other thing is that each data set is controlled by a individual entity. So a central authority does not have any control over it. So it's in a way it's just like the web. So just like there's Google for the general web, there should be a Google for LOD.
Absolutely, I completely agree. And yeah, something else which we wanted to do was, if you look at the way in which you access any or you find any of the LOD data sets, you go to the website linkdata.org and you click on one of these bubbles which you can barely see now because the number of data sets is so huge. So be able to present them in a little better, in at least a slightly different way than You go on the website, you click on the SVG image, and then it takes you to that particular data set. So,
but there are services like, as you mentioned, synthesis to Google. So these things do.
But you do realize that a lot of the data sets, so this is becoming an open question in the LOD thread, is that a lot of the data sets, they go down, and they're still made a part of this bubble and all that.
Right.
For example, I think there was one data set that was somewhere over here. It was related to bars in UK, and that went down like 4 or 5 years ago, and it still continued to be a part of it because nobody cared to even check it.
No, but I think I filled up the to ask the LOD CCAN.net. I filled it up like probably 6 months back.
Yeah.
When the newer version of LOD Cloud was about to come up.
Right.
So at that point of time, someone would have taken care of it, right?
So
it's like the manual specifications that users provide when they submit the data. So there is nobody who will remove it. When somebody submits the data, they would say, okay, this data set talks about users. And CCAN is based on that information.
So Richard Segniak, I think he's responsible for the.
So see and that's exactly the issue. You're talking. What Ajit was saying is that this is kind of the web, okay?
Right.
And web is not controlled by 3 people, okay? I know their names: Richard, Anja, and Chris Bisser. Okay?
Yes.
So you don't have a scenario where it's controlled by 3 people. I mean, this is a philosophical discussion, and this is an open-ended question.
No.
So
I am not talking about whether it can be controlled by 3 people or not. I'm just talking about when they were. I'm just surprised that the data sets which were not being.
And here's my point. Why do you have it manually? Why don't you have a system like DNS?
So basically the same. When I said Google doesn't ask you to publish.
Exactly.
It, right? Google does it by itself. So there has to be something that's at the same with LOD. So the cloud generation should probably be automatic. Now it's going beyond.
I mean,
stuff. Like
after a while, you'll probably need a microscope to look at your computer screen to see where's the bubble.
There was an interesting. I was in the Daxel meeting. They ran a Daxel meeting last week, and there were some cognitive psychologists there. So that was rather interesting. And one of them, in a brief talk, showed the development of this picture, and then asked for some brainstorming. What will this picture look like in 5 years? And so essentially, she said she came from a little bit of developmental psychology, and kind of things evolve, and groupings, grouping of information, how we group information changes, our conceptualization changes as soon as things mature. And can we get this over to this that she was actually saying? This is kind of object stage, right? Toddler stage. Right. So what would be grouping mechanisms which would make sense in 5 years? And I found that interesting.
So I was really young when the web started, but what I've heard is initially, even for the web, they had a directory where they had a list of websites, and you would go and find if the website was there, then you would click on it.
Yahoo used to do it with people, right?
Second?
Yahoo used to do it with people. There'll be guys sitting down and looking at things and then manually entering.
There are 9,000 people at one time.
Right,
and then that soon went out of hand.
Yeah, but I don't see that thing this is going to continue in this state, based on what I can see.
I think if the handle on quality is not there, it's not going to go anywhere. In fact, it can break down very easily, right? Because if the perception changes that people are not using it, and as that example of the amount of data that, that Watson found was very limited, then it would be a problem. Now, it's possible that there are some very good quality items in there. So being able to search them and then identify high quality items and use them, potentially like link drug LODD, then it may be fine.
Yeah, and that is actually happening for Google Knowledge Graph. It's actually based on Freebase. They're not openly acknowledging it, but that was part of the reason for their acquisition, and they're actually getting data from there. So it is happening that isolated chunks are being used, but as the entire corpus. Don't think so.
But I think people are more concerned about generating data than using it on linked open data. So once you start thinking about how to use it, that is when the whole cloud will start decreasing it. Then people will.
Yeah, it's basically how big my bubble can be.
Yeah, that is. You start streaming Twitter or.
That is what you're doing actually. So you're criticizing your own data.
That's the reason we are not publishing all these streamed data. If I start publishing the whole linked open data, one cloud will be of Twitter.
Linked open numbers. Right. Any more questions, comments?
All right. Thanks, guys. Let the committee chat a little bit with Prateek.